Hello everyone, and welcome to this demonstration of Factorial ANOVA. I am Dr. Vahid Aryadus from the National Institute of Education of Nanyang Technological University, and I'm delighted to discuss Factorial ANOVA today. So Factorial ANOVA is any kind of ANOVA that includes at least two variables, like this. So if it has two independent variables, if it includes two independent variables, we call it a two-way ANOVA. If it includes three independent variables, we call it a three-way ANOVA. So in this presentation, I'm going to show how we're going to run a two-way ANOVA on across stream and gender on a dependent variable, which is the writing scores of students. This kind of ANOVA that I'm going to do is also called 3x2 ANOVA, because stream has three levels: normal technical, normal academic, and express. And gender has two levels, that's male and female. Thus the term 3x2 ANOVA. A 3x2 ANOVA is a two-way ANOVA. Now another example here is a three-way ANOVA, where the first independent variable whatsoever has three levels. The second independent variable has three levels as well, and the third one has two levels. Thus a 3x3x2 ANOVA, or a three-way ANOVA, or a factorial ANOVA, or a factorial three-way ANOVA. You can really use either to refer to this kind of analysis. For this, we can imagine that we can analyze nationality for the first one, nationality with three streams, with three categories, stream for the second one, and gender for the third one. So I'm going to demonstrate how to do the analysis of a two-way ANOVA, which is a factorial ANOVA, using GLM, or General Linear Model, on SPSS. I'm going to choose Univariate for this demonstration. For our dependent variable, as mentioned, I'm going to choose the situational writing score. This is a writing task which was administered to students in secondary school in Singapore. And our fixed factors, or independent variables, are stream and gender. Stream has three levels. If you have not watched previous videos, I think I'm going to go through this quickly. This is stream, which has three levels: normal technical, normal academic, and express. And gender, as you can guess, has two levels only: females and males. Under models, I usually do not change the defaults. Full factorial design is very desirable in my case, because it's a factorial ANOVA, as mentioned. However, sum of squares, which is by default type 3, should be changed to type 4. And the reason is that I have some missing data in this data set. So type 3 and 4 are useful for factorial designs, but if you have missing data, type 3 is not very suitable. Type 4 is. So I'm going to choose this. You could build terms as well, I mean, if you're interested. For example, you just want to look into the interaction, the effect of interaction of stream and gender. For example, stream and gender interaction. This is a drop-down menu. You could choose interaction and that. So then in the analysis, the effects of stream and gender separately will not be estimated in the model. You will only get to see gender times stream. But I'm not going to do this for this demonstration, because I need to get a full factorial model where I get all sort of main effects and interaction effects. I'm going to explain what those effects are. In the previous video, I explained what contrast is, a long story short, contrast provides you with very similar information to post hoc analysis. But I also provided more details. Please watch that video for more details. Plots are very useful. I usually create two plots if I have two independent variables. I move the first variable to the horizontal axis, and then I populate separate lines with the second one and add. Now for the second plot, I shift them around. I shift them around in the sense that I move the second one to the horizontal axis and the first independent variable to the separate lines. So separate lines in this analysis will be represented by three streams, which was mentioned before. You could include bars, error bars, but I'm not going to do this because I don't feel that it's necessary. It's just some extra information. For post hoc analysis, we should keep in mind that this analysis is done only on variables which have 3 levels or more. So stream makes sense, but if I move gender, I could still get post hoc. I could still run the post hoc analysis, but the thing is, gender and stream. But the thing is, I will also get a warning, which will tell me that post hoc tests were not performed for gender because gender has only 2 levels. So I don't really see a need for that. Therefore, I stick with this stream. I'm going to use Tukey or Tukey equal variance as assumed way of estimation and click continue. EM means, well, basically it also provides you with the mean scores of the overall mean scores and the mean scores of each of the streams, but also provides you with a chance to compare the main effects of each. You could do that through Bonferroni correction because it makes some confidence interval adjustments. So this is what I usually do. Again, the type of information which is provided here overlaps partly with the results of post hoc analysis. These two therefore have some overlaps and also contrasts. But the overlaps are not exactly the same. You'll see in the results of this analysis. So I'm going to click OK or continue. For save, I have presented the uses of the save button or the save option. I have explained how standardized residuals can be used in order to investigate one of the assumptions of ANOVA. So I'm not going to do this for this presentation. If you're interested, look at that in the previous video. Options are important. You could choose descriptive statistics. I'm not going to do that because there will be too many tables. I'm just going to click estimates of effect size or partial eta squares and homogeneity tests. I think that's just good enough for this presentation. And OK. So what we're going to do is to go through every output of SPSS. In addition to that, I'm going to highlight the fact that you will need to look particularly for 3 blocks of information. One is the results of the Levines test of the homogeneity of variances. 2 is the tests of between subject effects, and 3 is the post hoc tables. Post hoc tables will be generated if tests of between subject effects are significant. So these 3 pieces of information are important, and you will need to report them in your papers or dissertations or thesis if you are writing anything. But I think it's also equally important to take a look at the descriptive statistics of your data, just to get a feel for your data, which starts from here. This part is the syntax. I'm going to explain this in the following part of this video because I'm going to show you how to use syntax, which is pretty easy. Right, so the univariate analysis of variance starts from here with between subjects factors and the descriptive statistics. So the frequencies have been frequencies have been displayed here. For normal technical, we have 198 for participants. For normal academic, we have 476. And for express, we have more than 1,000 participants. That's 1131. This simply indicates that there might be some differences in the variance of these groups because of the differences in the in n, or the frequency. It's just really a hunch. We can figure out if that's true or not. For males and females, we have a better balance because they're almost the same. Almost, really, not exactly. So the variable gender is in a better position with reference to its balance in the sample size. Right, now I'm going to move down to Levine's test of equality of variances, or error variances, if you will. And the first thing that I observe is that, well, this significance value is smaller than 0.05, way smaller than that if you go by mean. Of course, median and others also return the same thing, the same results. This is an indication, as I mentioned in the previous video, that the equality of variances, which is one of the assumptions of ANOVA, has been violated. Now, there are two schools of thoughts. Some people who have a more liberal idea about ANOVA would say you can go ahead and look at the rest of the results, but acknowledge this in your paper. Acknowledge that the Levine's test of equality of variances was significant. This is a more liberal view, because you can still go on and look at the results of the analysis. Another school of thought, which is not that liberal, and to some people it might sound a bit stringent, is that you're going to have to stop here and just do a nonparametric test, which I have also mentioned before, which is right here. Nonparametric tests and k-independent samples. But in this analysis, I'm not going to do this. In a different demonstration, I will show you how to do it. So let's pretend that these are not significant, or let's just adopt the more liberal philosophy of doing ANOVAs, meaning that we acknowledge that Levine's test of equality of variances was significant, but at the same time, we just went on and looked at the rest of the results. Okay? And we have to acknowledge that as well in our reports. So what happens is, after Levine's test of equality of variances, the first thing that we need to look at is this table. It's an important table, the test of between subjects effects, because it demonstrates two types of effects for us in a factorial design ANOVA. One is the effect of the first independent variable. We call this the main effect. So we have two main effects because we have two independent variables. That's main effect 1. And the second one, the main effect 2, is for gender. I'm going to represent the interaction effects of gender, of stream by gender, in a different color. Now, there are a few pieces of information which are important here. One of them is the F value, which for stream is much greater than 1.96. I'm not surprised to see that it's significant. The partial eta square is 0.181, which indicates that around 18.1% of the situational writing scores, which is our dependent variable, is explained by stream. That is, variance, 18.1% of the variance in this variable is explained by stream. This amount is arguably almost of medium size, because something around 0.2, or I should revise myself, I'm sorry, it's still weak because it's about 0.2, which is weak. But you could argue that in our field, getting a weak size of 18.1% is pretty much noticeable. For gender, the effect is significant, as you can see by the p-value here, 0.00, and it's much smaller than that. But the partial eta squared is about 4.3%. That is, 4.3% of the variance observed in situational writing total scores is explained by gender, which is probably not very noticeable. But for stream times gender, we see that there is no interaction. So if there were any interactions between gender and stream, then the results of the main effect analyses of stream and gender would not be reliable anymore, would not be useful for us. So we would have to stick with only stream times gender. Therefore, in the post hoc analysis, we would have to only look at stream and gender and not stream separate from gender. But that's not the situation now. Now, what I would like to remind you here is that quite a few pieces of information are repeated across different tables. So the first table that we're going to look at is the first groups of table, I should say, is the estimated marginal means, and it starts from the grand mean, that the mean, which is the mean of all the mean of our dependent variable, regardless, that's the situational writing total, regardless of the streams or of gender. So it's going to be something like this. So the mean score of this variable, so this is, let's say, this horizontal line indicates mean. Let's say that the mean score will fall right here. Right here. Okay. This is grand mean. Now we can break down the grand mean into streams. And you might say, okay, the grand mean is here. It's 11.031. Now the mean of the normal technical is 8.26. So let's assume it is right here. So it's the mean of the normal technical. That's the first one. Now I'm going to use a different color to represent normal academic, which is pretty close to the grand mean this time around. So I'm going to represent right here. Okay, so this is going to be the second one. If I could, I would write normal technical here, and normal technical here, and normal academic here. Sorry, I think I just made a mistake. This is normal academic, not normal technical. This is normal in the same way. This is normal academic, and grand mean under this one. But this software, from what I know, doesn't allow me to do that. I apologize for that. So I'm going to choose a different color for express. And express, as you see, is way above the grand mean. That's around 14, whereas the grand mean is 11. Just underline this. So the other one will go right here and here. Now what I could do is really to connect them using a line like this. As you see, the line simply shows that the mean score of the three streams increase as you move down this table. Okay, so that was just some descriptive statistics, really. And in our reports, we need to describe whatever I just described here, but you don't have to, really draw the lines and the bars that the graph that I drew, because that's just for presentation purposes. Now what we see is pairwise comparison. Just let's keep this in mind. A pairwise comparison is a comparison between the three levels. It's pretty much like post hoc. So look at, it's like a t-test. pretty much like the post hoc analysis. So let's compare this with the post hoc tests. Normal technical versus normal academic and normal technical versus normal express has a significant difference. We already know that normal technical has a lower mean score than the academic. Therefore, this significance value is in favor of normal academic. In favor meaning that normal academic has a significantly higher mean score than this. And express also has a significantly higher mean score than normal technical, and so on and so forth. So it's important to remember these and report them. Now I'm going to quickly scroll down to find post hoc analysis. You see more or less the same. It's actually the same kind of analysis. Right? You can just see that the mean differences are exactly the same as those in the previous pairwise comparison table. See, minus 2.494, 2.49. Right? It has 2 decimals. Actually, you could click on this and right click, cell properties, and add 1 more decimals just to, well, this is 2.92, 2.492, and it's slightly different actually. Here it's 2.4. It's slightly different, but the differences are negligible. And the reason I suspect is because it has used Tukey. Tukey might have adjusted for the mean differences in some ways, but that's really negligible. At 2 decimal values is really negligible. They're the same, but the significant differences are the significances of the differences remain way below 0.05 or even 0.01. So in the same way, you can find, and this is the univariate test, pretty much like an ANOVA test. Let's just here highlight this F value and significant value. Do you remember this? 198.001, which is here, stream 198.001. Okay, so I'm going to move down. For gender, you can see the mean scores. The mean score of males is lower than mean score of females. And is this observed difference significant? Yes, it's significant at this p-value, which is pretty small. Now you can see the univariate test for this as well. Does the F value ring a bell? We have already seen it in the previous tests of between subjects table right here, the 80.368 with a significant value of 0.000 and much smaller than that, and the partial eta squared of 0.043, which is exactly what you can see. What I'm trying to do here is to remind you that the output of SPSS includes a lot of repetitive information, so don't get confused if you see a lot of different information here and there. And finally, we see the interaction analysis, but unfortunately SPSS does not provide the pairwise comparisons. For gender, we have pairwise comparisons, as you see. For stream, we have the pairwise comparisons in post-hoc analysis, but unfortunately it's not so for secondary school stream times gender. That's the interaction. But is there any way to get SPSS to output this pairwise comparison for interaction effects? Yes, there is, and in the second part of this video I will explain that. So I'm going to pause here because this video is already long, and I'm going to continue discussing the rest of the results in the second part of the video. Thank you very much for your attention. If you like the video, give it a like please, and subscribe to the channel.